Okay, hey, so everybody, welcome to week 11. The semester is actually is winding down before our eyes. So we're going to talk about organic waste today. I wanted to start off with a few things. I want to talk about, just review cellulose. We did a whole week on cellulose. I'm just going to briefly review that. I'm actually going to dive into the periodic table a little bit and show you what elements are typically found in organic matter, meaning living organisms, plants and animals, because that's the broader lesson here. I'll also show you a few kind of freaks of nature that have taken advantage of waste streams in their environment, and show you also kind of my big picture on organic versus inorganic waste, and then just open it up for questions. So let's just take one more look at cellulose. I'm going to hop back out here. And I really think it's important that we dig down into the molecular structure. So I'm just going to show a few I'm just going to click around a little bit and show you what this stuff looks like. As I may have mentioned, I used to do some cellulose research. In fact, I just saw a pretty cool image. Let me grab that one. Sorry if I'm flying around here too much, but let me. Yeah, I clicked on this one. Oh, and there's so many ways this can go. This is what it looks like either under like an electron microscope or an atomic force microscope. So the cellulose itself harkens a little bit to that HDPE we were talking about, so long chains of molecules. What are those molecules? Well, very similar to the synthetics that we studied last time, a little more complicated. Each one of these little blobs right here, each one of these little carbon rings is, well, there's 5 carbons, so 1, 2, 3, 4, 5 carbons, 1 oxygen in that ring of 6, and then an oxygen bridge, an oxygen cross-linker that holds those together. And just so we're all clear on the chemistry. Let's go back. So we're clear on the chemistry. I want to show you where these bonds are coming from. So I just showed you that oxygen was the cross-linker there between those glucose molecules. So again, if we look at oxygen, I'm going to look at the orbitals, click on oxygen right here, and you can see right in the middle of the screen there are 2 empty electron shells in that 2p orbital. So it's exactly those 2 empty shells that allow this to happen, that allow that little oxygen to bond to sugars. And in this case, these are glucose monomers. They are assembled, and I'm forgetting the name of the enzyme. Anyway, they're put together in a plant. So a plant assembles this for its own structure. So the plant, first of all, is making the glucose, then it's assembling these polymers, and that is more or less the skeleton or the backbone of the plant, if you will. Okay, now, some organisms can digest cellulose, and the enzyme for that, I'm almost positive, is called cellulase. And there are several of them. So cellulase is a group of enzymes that acting together hydrolyze cellulose. So break apart cellulose with water. And so these guys are much more complicated molecule. This is a protein. It's going to be sitting in the gut of a cow, and it's going to break apart those long cellulose polymers convert it to starches, convert it to glucose, and eventually run the cow. Human beings do not have this enzyme. If we did, we could just skip the cafeteria and just head out to the soccer field for lunch. So anyway, okay. So just a little bit on cellulose. Also, the other really cool, amazing thing about cellulose is that you can turn it right into insulation. So that nice sticky fiber, it'll hold water. It'll hold a little bit of water. And so what we're seeing now in the building industry is those cellulose fibers. They'll put a little bit of water in there, get them stuck together, put a little bit of fire retardant, blow it into the wall. It sticks there, and now you've got a enhanced R value for a material that, well, goes in the trash frequently. I've got an example right here. So even this little shred of paper right here, could have been ground up, and instead of becoming a methane. Now, there will be cellulase, anaerobic cellulase microorganisms sitting in the landfill that will eat this piece of paper and turn it into methane, just like it would in a cow's gut. But instead, if we take it, shred it, then it becomes an energy asset rather than a global warming liability. Okay, so that's cellulose. I just want to review that a little bit. Now I want to go into all of the organic elements, and there are more than you think. Let's just look up the definition. And I'm sure everybody's going to have their own little definition. Let's go into ChemWiki. I've used them before. They're at UC Davis. Carbon obviously is the most obvious organic element. So that's listed first right there. Carbon-containing compounds. There we go. Okay, and they've got a nice, tidy little set of elements. Typically, I just mentioned proteins, for example, as for cellulase, an enzyme. A lot of times, proteins are just given the nickname of CHON, C-H-O-N, because the majority of all organic molecules are comprised primarily of carbon, hydrogen, oxygen, and nitrogen, or CHON, C-H-O-N. A little bit of fluorine. We know that chlorine is an ion that's actually used in neural transmission. Since I mentioned it, that's also the case for sodium. It's also the case for potassium. It's the case for calcium. It's the case for magnesium. You will hear of people taking lithium once in a while for mental disorders. It's not typically thought of as an organic element. It's something that's put in doses to compete with these other ions that are naturally in your body, in a similar way that any other drug is competing for a binding site inside your body. Typically, boron, no. Aluminum, not so much. We should, however, go up and look up the USDA recommendations for aluminum. Because there will either be a minimum that you should have, I know it's the same case for selenium, or a maximum you should not have. We can pop out the toxicological profile, because you're not going to see aluminum on the back of your vitamin bottle. What's that? You will see it in your deodorant. Yeah, you'll see it in your deodorant. You'll see it in your sunscreen. Yeah, yeah.
But they put it in our food.
And almost all your health.
Yeah, like baking powder.
Beauty, health shampoo, health deodorant.
Well, yeah, and it is mentioned here, aluminum found in over-the-counter medicines, antacids, aspirin, food additive, and we did mention topical consumer products as well. Okay, so here's what I was looking for. Based on the FDA's 1993 Total Diet Study Dietary Exposure Level, the authors estimated daily intake, so 1/10 of a milligram per kilogram per day, 3 times that much for 2 to 6-year-olds, not quite as much for 10-year-olds. I guess this is because they quit putting things in their mouths once they get a little bit older, and then on up the ladder.
So does that mean that, this stuff is known to cause horrible things.
Mm-hmm.
So are they saying you can take that much before, you're at risk of getting? How can they really say that?
Well, the first thing to keep in mind is that if you just go out and eat a chunk of aluminum, most of it's going to pass right through you. So it says right here, GI absorptions of aluminum is low, generally in the range of 0.1 to 0.4% in humans. Although, and here's the although, absorption in bioavailable, meaning something that your body recognizes, like, hey, aluminum citrate, could be much higher.
Because deodorant goes into your skin, goes into your pores, goes into, so there's like diaper rash
Yep.
stuff.
Yep.
When you cook with it,
Yep.
baking powder, it goes in, you're digesting that. So it has to be metabolized at that point, wouldn't it?
Well, so use the word metabolize. Metabolize actually implies that you're using it in some way, but
Or being broken down in your body.
yeah.
It'd probably be more scrubbed by your liver more likely, I would.
Yeah, no, the aluminum, once it gets in there, is going to be, and I wish I were more of a endocrinologist or a immunologist to know.
How long does it take to get out of your system?
Well, that's a great question too. Toxicity, like radioactivity, is an exponential function. So it's going to have a half-life in your body. You're never going to get rid of all of it. That's just so saying how long does it take to get out of your body? The answer, the truth is never. I mean, there's always going to be some kicking around.
The government's been killing us for years.
You actually get more radiation from the sun. Air travel is very.
Yeah, when the sun hits the aluminum in my body, in my pores, and causes this reaction.
So here are the this is what I'm most familiar with. Are neurological effects, psychomotor, so just how your muscles act, how you think, and other neurological symptoms. It does say that having up to 30 to 50 milligrams is kind of the max you can expect to have. I'm sure there are people walking around with 10 times that much that are just fine.
But this is the other thing. They know that this stuff is.
We know.
Who knows?
We know. We know.
But we still continue to put that into our body and our lives, knowing that this chemical is there.
Well, that's true of anything, though, Shelley. I mean, that's true of drinking alcohol. It's true of smoking. That's true of chronic marathon running. I mean, I don't think we're going to solve human behavior issues in this class. I think what it is important, though, is to be aware of what the toxic levels are and make sure that products are labeled appropriately and steer clear of things that you don't want to use.
One cupcake a day. Okay, well, I'll have to wear deodorant then. Just let you know.
I'm sure there are aluminum-free deodorants.
But it probably-
Now, if you get like a tox screen blood test, will it show, they probably don't test for most of this stuff, or do they?
No, right, just a normal blood profile, you would not see this.
Is there one available, you know?
Oh, absolutely, yeah, you could send your blood right over, we've got a lab here on campus, I'm not sure if they're qualified to do human testing or not, but, right here on campus that'll do, a full elemental analysis of all heavy metals. I do know somebody here in town who recently died of a copper, overdose. A certain amount of copper in your body is considered healthy. I wouldn't go ahead and call it an organic molecule. It is used in a few proteins in your body, just like iron. I mean, you have to have iron, right? Iron's sitting right there in hemoglobin. On the other hand, you can have too much. So typically, when you get your blood profile done, they'll say, this is how much iron is in your body. This much is too low, this much is too high. So there's no one perfect number for everybody. There's always a range on all of these things. So is that clear in terms of how do you're never going to get rid of all of it, and you need, and some of these metals you actually do need. Yeah?
So I think maybe you should check out, seeing if your class can get tested for the metals in their body.
What's that?
As a thing for, you know.
Oh, I think that'd be a good thing to collaborate with the nursing folks on.
Have them take our blood to, well, you know, but to have a, you know, the UM do a analysis. I mean, it's recycling, we touch stuff just to see, you know.
It would be a good one. Yeah, it'd be a nice service. Yeah.
Yeah, you should work on it.
Okay, thanks. So, anyway, these are the primary organic elements. And as we saw last week with plastics, we're mainly dealing with carbon, hydrogen, and in some cases, oxygen. So the chemistry is actually, you know, in terms of the number of elements, fairly simple. What types of molecules get formed can be more complex. Okay, I next want to look at lipids. So fundamentally, and again, this is also quite simple. Every single one of these little vertices you see here is just a carbon atom. So fats themselves are just carbon, hydrogen, and oxygen. Now, where it gets interesting for us as recycling technologists is how do you triage these things into separate components so that you can then turn it into fuels. So the obvious, sort of most lucrative, obvious path for lipids, for fats, is biodiesel. And in that case, you're not worrying all that much again about the chemistry. You're just kind of setting it on fire, right? So you're just combining this long chain fatty acid with oxygen and making energy. It's pretty much as simple as that. I mean, to me, that looks a lot like octane. Octane is, in fact, then we'll write it out. I'm not going to use the pad today, but let's just compare that to the molecular structure of octane. And if you guys really get into this, take Brian Kern's courses, 241 and 244. He gets really deep into the chemistry of what he calls alternative fuels. So right there, how could it be any more simpler? Octane looks a heck of a lot like our fatty acids, triglycerides. And these molecules themselves serve a very important role inside our bodies. Let me show you what that is. This is actually quite cool, quite incredible. So this is the surface of an animal cell. all these funny little two-legged, one-headed beasts are lipids. They actually form the boundary between the inside of the cell and the outside of the cell. All these proteins sitting in there, frequently those will be actual ion channels, the things allowing sodium, potassium, et cetera, to pass back and through the cell. So right there, we've pretty much covered the three primary organic molecules. We've covered sugars with cellulose. We've covered proteins. We saw a few examples, and here's even more. And then we've covered lipids. I mean, those are the three primary organic molecules. So all of your compost waste is going to be one of those three things, either a sugar-based structural element, a lipid like we're looking at right here, or a protein. And getting back to organic, they're all just going to be some combination of these relatively few molecules. One last thing I want to show you, and then we'll take a little break, and I'm going to show you kind of another big picture thing. So if we go back to our periodic table, here's phosphorus. Phosphorus is pretty cool, and then it's got three unbound electrons in its 3p shell. Same exact thing is true for arsenic. It's just one shell larger, but it's got those three active electrons out there. Phosphorus, as you may or may not know, forms the backbone of DNA. As it turns out, and let me show you that before we get to the other one. So if we dive in here, that's a pretty good one. Here's your phosphorus sitting right here with three oxygens attached to it. These are the nucleic acids. So boom, right there, that literally is the backbone of life. And not too long ago, somebody came along and found that there actually are a few, and again, there's a lot of papers. I'm just kind of grabbing the easiest one. There are a few organisms that actually use arsenic instead of phosphorus in their DNA, just because it's there. Now, you're probably well aware of the fact that if you eat arsenic, in a sufficient quantity, you'll die. And I don't know all the molecular mechanisms for it, but I'm almost certain it has something to do with the fact that the arsenic is getting in right here and kind of screwing things up. You know, it's like, hey, here I am, phosphorus showing up for the party, and then kind of crash the party, DNA falls apart, and so do you. There's probably other mechanisms as well, but you can see how you wouldn't want a whole lot of that in your body. So, with that, I think we've covered carbohydrates, lipids and proteins, we've covered the organic elements, and now I want to get into some of the practical issues of sorting organic material from inorganic material. Take a quick break.